asked to show a tangent plane at various points to each surface given by the functions below. We will do this using the 3D Calc Plotter JavaScript app shown here at the bottom, and this is from the Exploring Multivariable Calculus site shown here. Let's open up the app and show the tangent plane. When the app is first opened, this is always the default surface it is graphed, given by the equation here on the left. And notice how this is the first function we're asked to graph to show the tangent plane. But to make it clear that the 7xy is in the numerator, let's put the 7xy in parentheses. Notice if we press graph, the surface doesn't change because the entry is equivalent. Next, let's make the surface transparent so we can more easily see the tangent plane. To do this, we click the magnifying glass at the top. Notice now the surface is transparent. Next, we click on the 2D trace plane, which is this button here, then the arrow to the right, and select Show Tangent Plane at Point. Notice the trace plane is the XY coordinate plane. Let's click on a point on this plane. When we do this, the tangent plane appears on the surface at the blue point. But notice right now, the positive x-axis is moving to the right, and the positive y-axis is moving up. Let's change the orientation of the surface so the orientation of the xy plane is the same. Let's rotate this surface so the positive x-axis is moving to the right, and the positive y-axis is moving up in this direction. And now let's animate the tangent plane along the surface. The plane is tangent to the surface at the blue point. So this gives a nice visual of a tangent plane to a surface. Just like we can think of a tangent line as a linear approximation to a curve in 2 dimensions, we can think of this plane as an approximation of the surface at the blue point. Let's graph our next surface, which is given by the function f of x comma y equals 5 divided by e raised to the power of x squared plus y squared. So let's clear this entry and enter 5 divided by, in parentheses, e raised to the power of x to the second plus y to the second. And now we click graph. The new surface is graphed, but we need to zoom out. We zoom in and zoom out using the plus or minus here at the top. Let's click minus to zoom out. And now we have a nice graph of the surface. If we want the surface to be more smooth though, we can change the number of grid lines. Let's change the number of grid lines from 30 to 50 and click graph. If we watch the top of this peak here, it'll become more smooth, which we see now. And now we click on a point in the trace plane. Let's click the point 2, 2, and the tangent plane appears at that point on the surface. And now we can animate the tangent plane along the surface. The plane is tangent to the surface at the blue point. Let's look at our last surface given by the function f of x comma y equals 2 sine y. So we clear this function and enter 2 times sine y. And click graph. Notice how we have a graph of a cylinder. Let's reduce the number of grid lines so we can more easily see the tangent plane. Let's change the number of grid lines back to 30. And click graph. And now we'll click on a point in the trace plane, maybe 2, negative 2, and now we'll animate the tangent plane. I hope this gives you a nice visual of a tangent plane to a surface. Thank you for watching.
Hello everyone. So what I'd like to do here is describe how we think about three-dimensional graphs. Three-dimensional graphs are a way that we represent a certain kind of multivariable function, the kind that has 2 inputs, or rather a 2-dimensional input, and then a 1-dimensional output of some kind. So the one that I have pictured here is f of xy equals x squared plus y squared. And before talking exactly about this graph, I think it'll be helpful if by analogy we take a look at 2-dimensional graphs and kind of remind ourselves how those work, what it is that we do, because it's pretty much the same thing in 3 dimensions, but it takes a little bit more visualization. So with two-dimensional graphs, you have some kind of function, let's say you have f of x is equal to x squared. And anytime that you're visualizing a function, you're trying to understand the relationship between the inputs and the outputs. And here, those are both just numbers. So, you input a number like 2, and it's going to output 4. You input -1, it's going to output 1. And you're trying to understand all of the possible input-output pairs. And the fact that we can do this, that we can give a pretty good intuitive feel for every possible input-output pair is pretty incredible. And the way we go about this with graphs is you think of just plotting these actual pairs, right? So you're going to plot the point, let's say we're going to plot the point 2, 4. So we might kind of mark our graph to here, 1, 2, 3, 4. So you'd want to mark somewhere here 2, 4, and that represents an input-output pair. And if you do that with, -1, 1, you go -1, 1. And when you do this for every possible input-output pair, what you end up getting, and I might not draw this super well, is some kind of smooth curve. And the implication for doing this is that we typically think of what is on the x-axis as being where the inputs live. This would be, we think of it as the input 1, and this is the input 2, and so on. And then you think of the output as being the height of the graph above each point. But this is kind of a consequence of the fact where we're just listing all of the pairs here. And now if we go to the world of multivariable functions, here I'm not going to show the graph right now. Let's just think we've got three-dimensional space at our disposal to do with what we will. We still want to understand the relationship between inputs and outputs of this guy. But in this case, inputs are something that we think of as, a pair of points. So you might have a pair of points like 1, 2, and the output there is going to be 1 squared plus 2 squared, and what that equals is 5. So how do we visualize that? Well, if we want to pair these things together, the natural way to do that is to think of a triplet of some kind. So in this case, you'd want to plot the triplet 1, 2, 5. And to do that in 3 dimensions, we'll take a look over here. We think of going 1 in the x direction. This axis here is the x-axis. So we want to move a distance 1 there. Then we want to go 2 in the y direction. So we kind of think of going a distance 2 there. And then 5 up. And then that's going to give us some kind of point, right? So we think of this point in space, and that's a given input-output pair. But we could do this for a lot, right? A couple different points that you might get if you start plotting various different ones will look something like this. And of course, there's infinitely many that you can do, and it'll take forever if you try to just draw each one in 3 dimensions. But what's very nice here is that, here, I'll get rid of those lines. If you imagine doing this for all of the infinitely many pairs of inputs that you could possibly have, you end up drawing a surface. So in this case, the surface kind of looks like a 3-dimensional parabola. That's no coincidence. It has to do with the fact that we're using x squared and y squared here. And now the inputs like 1, 2, we think of as being on the xy plane, right? So you think of the inputs living here, and then what corresponds to the output is that height of a given point above the graph, right? So it's very similar to 2 dimensions. We think of the input as being on one axis, and the height gives the output there. So just to give an example of what the consequence of this is, I want you to think about what might happen if we changed our multivariable function a little bit, and we multiplied everything by half, right? So I'll draw it in red here. Let's say that we have our function, but I'm going to change it so that it outputs 1/2 of x squared plus y squared. What's going to be the shape of the graph for that function? And what it means is the height of every point above this xy plane is going to have to get cut in half. So it's actually just a modification of what we already have, but everything kind of sloops on down to be about half of what it was. So in this case, instead of that height being 5, it would be 2.5. You could imagine, let's say we did this, it was even more extreme. Instead of saying 1/2, you cut it down by like 1/12. Maybe I'll use the same color. by 1/12, that would mean that everything, schloops very flat and close to the xy plane. So a graph being very close to the xy plane like this corresponds with very small outputs. And one thing that I'd like to caution you against, it's very tempting to try to think of every multivariable function as a graph, because we're so used to graphs in 2 dimensions, and we're so used to trying to find analogies between 2 dimensions and 3 dimensions directly. But the only reason that this works is because if you take the number of dimensions in the input, 2 dimensions, and then the number of dimensions in the output, 1 dimension, it was reasonable to fit all of that into 3, which we could do. But imagine you have a multivariable function with, a 3-dimensional input and a 2-dimensional output. That would require a 5-dimensional graph, but we're not very good at visualizing things like that. So there's lots of other methods, and I think it's very important to kind of open your mind to what those might be. In particular, another one that I'm going to go through soon lets us think about 3D graphs, but kind of in a 2-dimensional setting, and we're just going to look at the input space. That's called a contour map. A couple other ones like parametric functions, you just look in the output space. Things like a vector space, you kind of look in the input space but get all the outputs. There's lots of different ways. I'll go over those in the next few videos. And that's 3-dimensional graphs.